Welcome to Course 101, TiDB Technical Essentials. This is Module 7, TiFlash. My name is Jeff and I am your instructor for this module. After completing this module, you will be able to describe the TiFlash architecture and understand the main functions of TiFlash. TiFlash is a key component of the TiDB HTAP story. Recall that TiKV is a row-based storage component and TiFlash is its columnar counterpart. Another way to say this is TiFlash is a columnar storage extension of TiKV. It provides good isolation and strong consistency. In TiFlash, the columnar replicas are asynchronously replicated according to the Raft Learner consensus algorithm. When these replicas are read, the snapshot isolation level of consistency is achieved by validating Raft index and multi-version concurrency control. This architecture solves the problem of isolation of HTAP scenario synchronization of the column store as well. The diagram shows the TiDB HTAP architecture. If you look at the bottom left, you will see 3 TiKV nodes. Scan towards the right and you'll see 2 TiFlash nodes. TiFlash provides a very efficient coprocessor layer. Remember, the coprocessor empowers TiDB server to push processing down to the storage layer. In addition, it is very similar to TiKV and relies on the same Raft region for data replication and distributes data in regions. TiFlash replicates the data in the TiKV cluster in real time with low consumption and does not block TiKV writes, and at the same time provides consistent read like TiKV and ensures that the latest data is read. The region replica in TiFlash corresponds exactly to TiKV and will be split and merged at the same time as the leader replica in TiKV. TiFlash replicates data on a table-by-table basis. In fact, an alter table SQL command is used to set up the replication relationship. TiFlash is compatible with both TiDB Server and TiSpark, and users can choose to use different computing engines. PingCap recommends that TiFlash run on its own nodes because it ensures workload isolation. However, in a pinch it is acceptable to deploy TiFlash on the same nodes as TiKV. In the event that TiFlash cannot replicate data, any data written to TiKV will be synced to TiFlash at a later time. TiFlash accesses the TiDB cluster as a Raft Learner. This is an extension of the Raft algorithm. Here's some trivia regarding TiFlash. TiFlash cannot withstand high concurrency, and the average query per second cannot be higher than 50. TiFlash's region is exactly the same as TiKV, and the partition is the same. TiFlash is suitable for scenarios where the entire table or most of the data in the table must be read. And finally, TiFlash performance improvements are in column store, aggregation, and join. TiFlash has several core features. We will look at 4 of them here. They are asynchronous replication. Replicas in TiFlash perform asynchronous data replication using a special Raft role, learner. This means that when a TiFlash node goes down or the network has high latency, TiKV can still ensure normal operation. This replication mechanism also inherits the automatic load balancing and high availability of the TiKV system. It does not rely on additional replication pipelines, but directly receives TiKV data transmissions in a one-to-many manner. As long as the data in TiKV is not lost, a replica of TiFlash can be recovered at any time. Next, consistency. TiFlash provides the same snapshot isolation support as TiKV and ensures that the read data is up to date. This consistency is achieved by verifying the replication progress of the data. Each time a read request is received, the region replica in TiFlash initiates a progress check. This progress check is a very light remote procedure call to the leader replica and only responds to reads when the progress ensures that it contains at least data covered by the timestamp of the read request. Intelligent engine selection. TiDB server can automatically choose to use TiFlash or TiKV row store, or even a mix of the two within the same query to provide the best query speed. This selection mechanism is similar to TiDB server's selection of different indexes to provide queries. It is based on statistical information. The read cost is judged and a reasonable choice is made. And finally, acceleration of calculations. TiFlash's computational acceleration of TiDB is divided into two parts: the read efficiency improvement of the column store itself and the sharing of computation for TiDB. The principle of shared computation is the same as TiKV's coprocessor. TiDB will push down calculations that can be performed by the storage layer. The ability to push down depends on whether TiFlash can support the push down task. Next, let's discuss asynchronous replication. The diagram shows TiFlash participating in TiKV replication. First of all, we know that the region data in TiFlash and TiKV's regions are the same, but only the column store version is used. Second, the region in TiFlash corresponds to TiKV's original Raft group as a learner to form a new Raft group. However, the region in TiFlash does not participate in voting or elections and is not counted as a member of the majority. That is, if a leader writes the majority follower, it can confirm that the data was written successfully, regardless of whether the learner node in TiFlash was written successfully or not. In this way, TiFlash's replication is asynchronous and the impact on TiKV's performance is tiny. Finally, TiFlash uses a fast update mechanism based on a primary key, so that although it is asynchronous, it does not have much delay with TiKV. Next up, TiFlash key features. Consistent read. Previously we mentioned that TiFlash guarantees consistency of reads. Let's take a look at this process. Here we use a series of diagrams to represent TiFlash's guarantee of consistency reads. Notice that at T0 the client writes two items to TiKV, key 1 and value 100, and key 999 and value 7. At T1, the client initiated a TiFlash read, key equals 1 and key equals 99. At T2, the client again wrote key 1 and value equals 200 to the cluster. This was a modify key equal 1 to 200. At T3, TiFlash checks the current sequence number using the Raft log index of the Raft log in TiKV in order to satisfy the client's read. It obtains the Raft log whose key equals 1 and has Raft log index value of 125 and key equals 99, the index value is 31. On the TiFlash side, we can see that we are waiting to add IDX equal 125 and IDX equal 31 to our flash data. At the T4 moment, TiFlash waited until the Raft log index of key equal 999 was 31 and confirmed that the value of key equal 999 must have been copied, so it read the value 7 of key equal 999. Next, at the T5 moment, TiFlash waited until the Raft log index of key equal 1 was 125 and confirmed that the value of key equal 1 must have been copied, so it read the value of key equal 1 but found that there were two versions, 100 and 200. Since the read occurred in T1, the value from T2 is discarded and returned to its previous value of 100. TiFlash key features. Engine Smart Selection. As a coordinator, TiDB server can evaluate queries based on the SQL that was submitted. Using this evaluation, TiDB server automatically chooses whether to perform the work on either TiKV or TiFlash. Or, as shown in the diagram, TiDB server can direct TiKV and TiFlash to read the data. This is an example of a query that accesses both TiKV and TiFlash. Since there are no product table columns used in the select list, PID and batch ID are the only product columns used, and they are on the where clause. Fortunately, these columns are covered by an index on PID and batch ID. This means that TiDB server can choose to read the index in TiKV to filter out the data of the product table that meets the condition. The sales table takes the price column for aggregation. This is an average, and there are no filter conditions, which is equivalent to a large table scan. So it is more suitable for table scanning in TiFlash. In the end, the two channels of data that meet the conditions are summarized on the TiDB server to arrive at the results. So, index lookup on the TiKV side, table scan on the TiFlash side. We have covered a lot of material during this module. I feel confident that we have met all of the objectives defined at the beginning of this module. We can describe TiFlash architecture, and we can understand the main functions of TiFlash. Thank you for taking the time to view this module. We hope you have enjoyed it and learned a lot.